A very good morning to all the participants and our distinguished speaker. I am Vinita Anvekar. I, on behalf of SAXS CRNTS IIT Bombay, take this opportunity to welcome you all for today's talk on small angle X-ray scattering titled Structural Characterization of Soft Matter using X-ray Scattering, which will be presented by Professor Kamendra Prakash Sharma. Before we proceed, I will begin with an overview of SAF IIT Bombay. SAF IIT Bombay was inaugurated by our late ex-Prime Minister, Shri Morarji Desai, in year 1976. SAF was established at IIT Bombay with the DST support in the year 1976. Center for Research in Nanotechnology and Science, popularly known as CRNTS, was established at IIT Bombay with the DST support in the year 2006. In the year 2008, both SAF and CRNTS were merged and it came under one umbrella, which is led by one in charge. Currently, Professor Anil Kotantrayal is the head of the department. We have around 16 major equipment in SAF and around 6 major equipment in CRNTS. SAF IIT Bombay provides measurement services to IIT Bombay students as well as to the users from various academic institutes, national laboratories and industries. CRNTS also has an academic wing which has more than 65 associated faculty members and more than 80 PhD students. DST has set up SAF in various parts of the country with the objective of providing guidance for the data acquisition using sophisticated analytical instruments. During the financial year of 2019-2020, SAF IIT Bombay had more than 2,700 users and we have analyzed more than 25,000 samples. The current slide shows you the facilities at SAF IIT Bombay which are funded by DST, of which small angle X-ray scattering is the topic of our talk today. We have upcoming dual beam FIV FEG SEM which is under installation. This slide shows the facilities at SAXS CRNTS which are funded by the institute. This is small angle X-ray facility housed in SAF IIT Bombay. Dr. Gajendra Saini is the in charge. This instrument is of Xenox make and model is Zeus 2.0. It has dual X-ray source. We have accessories for various sample environments such as capillary holder, high temperature sample stage which can range from -150 to 350 degrees Celsius, tensile stage, multi-purpose X-ray temperature stage, powder holder, GI SAXS holder and pressure cell. You can visit us at saf.itb.ac.in wherein the information of all the instruments housed in SAF IIT Bombay are available. Also, you can get the procedure to avail these facilities. We get samples from all the states of India as well as from our neighboring country, Nepal as well. We encourage visitors from various academic institutes, national laboratories and industries. You can join us on our LinkedIn to get the latest update on instrument, webinars or any upcoming events held at SAF IIT Bombay. This is a brochure for the ongoing series, webinar series, information for which is listed on our LinkedIn page as well as on our SAF web page. This is a group photo of our SAF staff. We would be very happy to welcome you all and help you with the analysis. Now I introduce you to our today's speaker, Professor Kamendra Prakash Sharma. Professor Kamendra Prakash Sharma is currently an Associate Professor in the Department of Chemistry at IIT Bombay. He has obtained his PhD degree from National Chemical Laboratory, Pune, and has done his postdoctoral research from University of Bristol. His research mainly focuses on the design and development of multifunctional nanomaterials via non-covalent interactions in a concoction of soft matter entities like proteins, polymers, surfactants, nanoparticles, and liquid crystals. Professor Kamendra Prakash Sharma has published and co-authored around 28 research papers in international peer-reviewed journals. We are sure that this talk will enlighten the knowledge of researchers to use small angle X-ray scattering for their research purpose. Just an important note, queries related to today's talk should be posted in the question and answer box only. Questions with the participant's name only will be answered. We will be posting the feedback form. Kindly fill it. It will help us to improvise. So let us commence today's talk. Over to you, Professor Sharma.
Thank you, Vinita,
Yes,
for the
yes.
nice
Welcome.
introduction. And thank you, Professor Anil, for giving me this opportunity to speak about some of the work we are doing with the soft materials and specifically the usage of small angle X-ray scattering, okay, for characterizing our materials. So this talk, as you can see, the title of this talk is Structural Characterization of SAXS matter using, actually it should be small angle X-ray scattering, but I've just put down X-ray scattering for now. Uh, so, so today what I will start with, or like would like to give you the outline of my talk first of all. This talk is mainly focused on potential users who work in different areas of soft matter, okay, who are willing to use small angle X-ray scattering and utilize it to get different kinds of information, which I'll be talking about. I'll start with telling you what is soft matter actually, and how does SAXS come into the picture. Or SAXS is actually a short form of small angle X-ray scattering. Okay, and how does it compare with other techniques? So you can obtain similar information, but what is the difference actually? And what type of simple analysis you can do with small angle X-ray scattering? I'll touch upon these things a little bit, and then I'll jump on to examples of small angle X-ray scattering, different examples which we have been dealing with surfactants and its assemblies, nanoparticles, surfactant composites, liquid crystals and proteins, polyelectrolytes, as well as anisotropic nanoparticles. So I hope I'll be able to cover all these examples in the given time I have. But if I'm not able to, you please feel free to talk to me about this. My email ID will be available on the website. Yeah, I've also put down some recommended books for users who want to actually uh, uh, go about reading in detail about small angle X-ray scattering, and these are mentioned below. Okay, so let us start with what are soft materials actually. So if I have to understand what is a soft matter, it's actually soft matter actually talks about molecules which are large, okay, large in terms of they are assemblies of molecules. Okay, when I say large molecules, they you can immediately think about molecules which are long chains like polymers. Okay, or assemblies of small molecules which move together. Okay, so when they are collected at one place, their dynamics become much slower, and the entire assembly is known as a soft matter. So here I've listed down some of the examples which constitute soft matter. For example, polymeric materials. I'll just pull out my laser pointer. So polymeric materials in the solution, you can have paints. Paint is an example of a soft material, okay, because it's nothing but solvent and the soluble particles in it. All these liquid crystal displays into which you are looking right now constitute a soft material. Okay, surfactant, for example, this is an example of surfactant forming liposomes and vesicles or micelles. These are also a collection or assemblies of molecules, and they come under the category of soft material. Even the cell membrane, which is shown over here, constitute a soft material. The proteins, which are again large molecules, their size are many kilodaltons in terms of molecular weight, they also come into the category of soft materials. So these materials have certain property that they show a collective behavior. The dynamics are fairly slowed down as compared to very small molecules. They show very large or non-linear response to any sort of perturbation which is imposed on them in terms of, like, for example, if I change the temperature a little bit, the properties might change significantly. So these class of materials are known as soft material, and this is what my group deals with right now. And so we work with different kinds of materials. This is one slide I've just put down to show what we actually do in our lab. So this is on the top left, you have example of these micron-sized droplets made up of liquid crystals and proteins. So the reason they are looking the red, green, or yellowish is because they have these fluorescent dyes in it. So these are liquid crystal droplets, and these are microns in size. They also constitute a class of soft matter. Another class of material which we work with is proteins covered with polymers. These are, and they form these gel type of samples. So essentially this gel or this liquid, whatever you're seeing, is made up of proteins covered with polymers. We also work with nanoparticles coated with polymers, and these nanoparticles can actually sequester gases. Okay, so they can be used as liquids, but they can actually they can also like store gases. Another class of material which we are working with is like polyelectrolytes and their self-assembled structures. So I'll be talking to you about these structures in a bit. Okay. Now coming back to, like, we use small angle scattering, X-ray scattering, as one of the tools to characterize these materials, which I showed you in the last slide. So this is one of our tools. So this is not the only tool which we use, but what small angle X-ray scattering provides you is that is based on this definition which I had picked from this book from Otto Glatter, who is a pioneer in small angle X-ray scattering. And what they say is that small angle X-ray scattering is a small angle scattering technique where the elastic scattering of X-rays between 1 to 2 angstrom by a sample which has inhomogeneities. These words are important: elastic scattering and samples having inhomogeneities. When I say inhomogeneities, when I'm talking about X-ray scattering, it means the difference in electron densities within the sample. So there is the electron density differs as you move within the sample. Okay, and inhomogeneities in the nanometer range are observed. Okay, the typical information which can be achieved is shape of the material, size of the system of macromolecule, characteristic distances, pore sizes, etc. Okay, and SAXS is capable of delivering structural information of the order of 5 to 25 nanometers for systems which are partially ordered up to 150 nanometers. Now, this was actually mentioned some time back, these numbers. Now, with the advent of new technologies, these numbers keep on shifting to higher values. Okay, so now you can obtain information up to 300 nanometers as well. Okay, given the new geometries we have. So, as Vinita has already shown you that there is a small angle X-ray scattering facility at IIT Bombay. This was installed a couple of years back, and it's a fantastic equipment. So here is the generator where the X-rays are generated, and they are collimated through these this beam path, and this is a sample chamber, and sample can be put over here, and so as the X-rays fall on the sample, they are scattered in different directions, and they fall on the scatter radiation fall on the detector. And I'll tell you what we do from here. So we have various types of sources for generating the X-rays. One is the copper source, one is the molybdenum source. So copper is used mostly for but if the samples have fluorescence, for example, metal, then you can have molybdenum source. And we have a state-of-the-art detector over here, which is Eiger R1M. It's a hybrid photon counting detector. It's and it's very highly sensitive. So this is like one of like state-of-the-art machine, which is I think so the best in the country right now. Okay, and we have various types of sample environments. We can put liquid samples, we can put solid samples at high temperature. We can actually take fibers and we can stretch it and do analysis on that. We can put we can go from minus 130 to 150 degrees Celsius. We can take powder samples. We also have a pressure cells. For example, if you want to see if pressure changes the properties or structure within your sample, then we can do all these things. And we can also do scattering. So all these examples for scattering in the transmission mode, but we can also do in the reflection mode, where the sample, when you want to analyze what is on the surface, you can always use a GI-SAXS, which is known as grazing incidence small angle X-ray scattering. Okay, now what is the information from SAXS you can achieve? So basic information is like you have how you do the experiment. You have this light source, rather X-ray source, and here this is your sample. It scatters, and it goes. The light goes onto the scattered light goes onto the detector. That is what the experiment is done. Now taking this scattered light and now reconstructing it to a picture is known as a reconstruction or the analysis part. So what that machine can do is this part. which is shown till this point. Okay, later when you take the data, this is what you have to achieve. It's like a inverse problem, right? So you have a shape or size or something of about the sample, and this shape and size of the sample scatters the radiation in some way, okay, which is unique or which is specific to the shape and size of this particular sample. So this scattered radiation you have to take and you have to reconstruct it into an image. That's the job of a person who's trying to analyze their data. So basically, information what you can achieve after reconstruction is shape, structure from the materials. Okay. Now, same information you can achieve from the transmission electron microscopy as well. Okay, but what's the difference in that? Okay, I wanted to just highlight that, see, if you can get the similar information in nanometer length scales or tens of 10 to 100 nanometer, you can do it from transmission electron microscopy also. But why SAXS is very important? Because in SAXS, so if so I just want to put down the pros and cons of SAXS as well as pros and cons of microscopy. So if I want to look at small details and local structure, then TM is the best technique. Okay, very, very local structure. For example, if I'm a god, I'm mammoth. Okay, right? I would like to map out the entire Mumbai. Okay, now if I want to map out the entire Mumbai, I can't do it with microscopy. I can probably pinpoint IIT Powai, a smaller area, and map it using TM. But if I have to map out the entire Mumbai, you need scattering. Okay, so scattering gives you a wide or an average value. Okay, it gives you an average value which microscopy cannot, TM cannot provide. Okay, now, there are also issues with sample preparation artifacts. So, scattering, small angle X-ray scattering is a non-invasive technique. You do not invade the sample as such. So, there is no issue. So, but with TM, there can be sample preparation artifacts. For example, drying can cause aggregation or some sort of changes in the sample, which might not be the exact property of the sample when it is in the original form. Okay, so that is where scattering comes into like very, very handy tool. Results. Now, if I want to interpret the results of microscopy, these are direct pictures. Of course, you can see the direct picture, how your sample looks like. So these are unique things. Okay, but statistics are poor, remember that. But here the results are like ambiguous, like you have to go back and interpret your data. Okay, it so happens many times that you have to combine microscopy and scattering as a combined tool or combined study to have a better understanding of your data. Okay, so they go hand in hand, so they are complementary to each other. So where microscopy cannot give the entire average information of the system, scattering can give you this. But to analyze the scattering data, sometimes you have to take help from the microscopy data as well. Okay, so now why small angle? What is wide angle and so on and so forth? So first of all, we need to understand when X-rays pass through an object, it causes the electrons to oscillate at certain frequency, okay, of the sample, and as that of the incident waves. So these oscillating charges give rise to secondary electromagnetic waves of the same wavelength. So because it is an elastic scattering technique. Now, any scattering process is characterized by a reciprocal law. So if you remember the Bragg's law, it mentioned N lambda is equal to 2D sine theta, right? Similarly, so theta is inversely proportional to D. So so what I'm trying to say is that if your scattered radiation is at low angle, so the D will be high. Okay, D is the size or the size window which you are looking at. Okay, or the dimension of the system you are looking at. So there can be two types of angles you can looking at: small angle, which is between zero point 0.1 to 10 degree, or wide angle, which is 10 to 170 degree. So it can be easily understood. If we are looking at wide angle, we are looking at small d's, or we are looking at crystal structures of the order of 1 to 10 angstroms. Okay, so less than a nanometer. But when we are looking at small angles, we are looking at large d values. That means we are looking at system between 1 to 300 nanometer. So that's why small is very important when we are trying to study nano. Okay, so wide angle X-ray scattering or normal X-ray diffraction is between 10 degree to 170 degrees, which will give you the crystal dimensions or the edge lengths, etc., but not the nano dimensions. Okay, so that's what I was trying to tell you. So what is small angle X-ray scattering, wide angle X-ray scattering, or XRD? So here Q is known as a scattering vector. It's nothing but theta only in normal diffraction language. Okay, it's related to it, but it has all the information about the wavelength of the radiation used or the X-rays used and the angles. And so Q is inversely proportional to D. Okay, as Q decreases, okay, you are looking at very large D values, 1 to 100 nanometers. Okay, as Q is high, that is XRD, for XRD, 10 to 170 degree, we are looking at something which are very smaller dimension. That is what we call X-ray diffraction. So basically, we are interested in small angle X-ray scattering. So we'll look at only small angle region. And by the way, this word scattering is rather used loosely. You can call it diffraction also, small angle X-ray diffraction or wide angle X-ray diffraction, because diffraction is a word which actually comprises scattering and interference, and the signal what you get on the detector is an interference of different scattered radiations. So people use it interchangeably, diffraction or scattering, but in my opinion, the correct word would have been small angle X-ray diffraction. Okay, yeah, I would just like to mention that in some places in my slides, so this Q will also be mentioned as S or H. These are essentially the same, but some people want to represent in the form of S or H. Okay, yeah, some of the questions which come into the picture is that what type of sample to be used. So what should be the thickness or what should be the concentration? So thickness or concentration of the sample depends upon their mass absorption coefficient. Okay, so some of the mass absorption coefficients I have mentioned over here. So just simply I would like to tell you that more the atomic number, okay, of the material, the absorption will be quite high. So you can see iron has a very like small optimum thickness which can be used or scattered or can be used for scattering the X-rays. Okay, yeah. So a typical SAXS experiment, you take the sample, okay, and you pass the radiation onto it, and then you have a scattered radiation on the detector. And this is a general equation of scattering. So what you obtain is the scattered radiation intensity, which is proportional to P of Q and S of Q. P of Q is known as the form factor of the system. It's actually the scattered radiation from a dilute system. But when you start concentrating that system, then there is this S of Q, which is known as the structure factor of the system, comes into play, which talks about the interactions between the materials. So P of Q will tell you the information about a single entity when it is dilute in the system, but S of Q comes into the picture when you start concentrating the system. So this is how a scattered data looks like. This is a particular image which has come onto the detector. You can see these yellow and red rings. Okay, now you take this data, you do the reduction and you do the analysis. Okay, that is what you do. Okay, now what do you mean by reduction? This is actually a 2D scattered radiation. You have to convert it into 1D. 1D data means you have to integrate. You can do either chi integration or 2 theta integration. Not important right now to understand much, but generally people do this 2 theta integration. And so as a function of Q is the, I told you, scattering vector, which is nothing but the angle, okay, where angle of scattering is 2 theta. And this 2D data is actually converted into 1D data, and this is what 1D data looks like. So when the operator gives you data, it will be something like this: I of Q versus Q, that is intensity versus Q, or intensity versus theta in simple language. Okay, this is what your data looks like. Now, this doesn't make any sense. Your sample might be having, for example, spherical nanoparticles or something rod-like nanoparticles or surfactant assemblies. But what is this? Okay, that is where your real journey starts. Okay, so this might be 5-minute collection or on, but you might now start looking into this and spend 5 years to analyze it. Okay, so this is like 5 minute collection time to 5 year PhD thesis for much complicated samples. I'm talking about the systems which are unknown for the systems for those systems where modeling is not very easy. Okay, so that's where I'm talking about. I do not want to scare you that every data takes five years, but essentially, like if you want to do a rigorous PhD onto this particular using small angle X-ray scattering tool for a particular type of system, it might take a long time. Okay, if the models are not known, because modeling is what gives you the desired result. Yeah, but typical SAXS data, what I told you is like something like this, intensity versus Q, and people plot it in the form of log I of Q versus Q to get these features seen better. Okay, now what information can you achieve from there? So yeah, I can take this data and now I can start pulling out information from it. Okay, the information which can be achieved is size, shape, surface area. Okay, essentially you can achieve radius of gyration, you can achieve shape. If their sample is porous, you can obtain porosity, you can obtain crystallinity in the sample, you can do absolute intensity measurement to get the molecular weight of the sample, you can find out the polydispersity, you can find out the correlation length, and so on and so forth. Okay, so these are the sort of information you can start retrieving it, and this has to be done by some bit of analysis. Okay, now there are various ways of analyzing the SAXS data. So some are model-free analysis, some are analysis using some specific models. Okay, I would just in my talk today, I would just like to focus on a couple of examples which are model-free. For example, over here. So if I'm trying to talk about model-free analysis, I need to remember this simple equation. Okay, that I of Q, that your intensity of the scattered radiation is equal to n times P of Q and S of Q. P of Q, as you remember that I told you, it is the scattering from a very dilute system, and S of Q is the scattering or in the contribution to the scattered radiation, which comes due to uh, by the interaction between these systems when they become concentrated, when they come close to each other, when you increase the concentration. For example, you take nanoparticles in solution and you start increasing the concentration. At one point of time, they will start interacting. They will start feeling the presence of each other. That is where structure factor kicks in. Okay, and N over here, I would like to tell you it's a combination of many things. For example, what is the electron density difference between in the sample? What is the volume of the scatter, etc. Okay, so I would like to tell you some simple model-free analysis. For example, one is Junior approximation. You get a scattered radiation data. For example, it is what it looks like. For example, you have nanoparticles in solution. Now you don't know what exactly is the shape of these nanoparticles, right? Now this Junior approximation, irrespective of what is the shape of the nanoparticles or what is the size of these nanoparticles, can give you one simple out of this simple analysis, which is known as the radius of gyration. Okay, so you take the scattered radiation, scattered data, log I versus here it is mentioned H. Of course, it can be Q square also, and you take a area in this curve such that Q times Rg should be less than 1. Okay, so you take this and you fit it to this universal law. Okay, and you get the slope out of it and you get the value of Rg. Okay, this Rg will be irrespective of what is the size and shape of the particle. So this is known as a Junior approximation. You can have the scatter, so you get the Rg of the system. And now if you know some shape of your particle by other means, for example, microscopy or TM, now you can now convert the Rg into R value very easily. Okay, so another type of information which can be obtained from the scattering curve is known as Porous analysis. Okay, this is again a scattering curve. So this is nothing but intensity again as a function of Q. And Porous law looks at the scattering at very high Q values. That is very high angles. Okay, and you can, if I have to fit this, if I put this high region and using this particular equation, what you can achieve is something which is known as the surface area of the system. So you can start thinking of it. Why did I now start getting the information about surface area? Because at very high Q values or very high angles, we are actually going to, if you are looking at the scattering from a nanoparticle at very high Q values, we are going to look at only very small area of the nanoparticle, and that has to be the surface. Okay, so we can, using Porous analysis, okay, the high Q data can be fitted, and that can and fitted by plotting IQ4 versus Q. Okay, and what you achieve from that equation is known as the surface area. If you want to know what is the surface area of the nanoparticles, maybe you can use the Porous analysis. Okay. There are other scattering techniques also, for example, methods also for analyzing the data, which is known as a generalized inverse Fourier transformation. To be specific, that to tell you that is, for example, you have a particle and you get a scattered data. So now you want to know what is the shape of your particle. Now this is an inverse problem. Of course, you are getting data in inverse space because the units of Q is per angstrom or per nanometer, right? You have to get data in the real space. You have to do something which is known as a inverse Fourier transformation. I will leave this particular thing right now, not discuss much about it, but if you are like very excited about reading about generalized inverse Fourier transformation, you can get this information from this particular book which is mentioned here. Okay, so now I'll quickly change the gears, and since I have given you a quick introduction about what small angle X-ray scattering can do, I would like to just give you that some of the examples we have used SAXS for the soft matter characterization. And these examples have been taken from a few of the publications over the years which my group and like before I joined IIT Bombay, I had worked on some soft materials. So these are listed over here. And if time allows that, I will be able to probably talk to you about till polyelectrolyte self-assemblies. Okay. Now, so surfactant is one class of soft material, and I told you that surfactant can form assemblies as well, right? Now, so surfactants are amphiphilic molecules where there is a head group and there is a tail, and they can pack differently depending on something which is known as a critical packing parameter. Okay, and this critical packing parameter can lead to different types of geometries of surfactant assemblies. You can have spherical micelles, you can have cylindrical micelles, you can have lamellar phases or something like this, or you can have inverted micelles. Okay, so these I just wanted to give you ideas about different types of surfactants, and or surfactants can form different assemblies, and these assemblies can be characterized by small angle X-ray scattering. And surfactants can, so when I'm talking about the geometries, they of course they can pack in different ways. So of course I told you molecule micelles. You can have hexagonal phase, these tube-like micelles. The cylindrical micelles can pack in the form of hexagonal systems, or you can have cubic phases, bicontinuous cubic phases. You can have lamellar phases. Now you can go into reverse structures also. So this is the normal type or positive curvature where your hydrophilic group actually is facing out and your tail is facing inward. Okay. But you can have reverse structures where your hydrophilic groups are actually facing in and hydrophobic groups are pointing out. Okay. So you can form these sort of structures. In terms of dimensions, I can again say that so micelles are actually 0D systems, lamellar phases like the surfactant forming these layers like membranes are 1D systems. You can have hexagonal phases, you have bicontinuous cubic phases, and so on and so forth. So this is one example of a scattering pattern from a hexagonal system of a surfactant. So if you take, I would just like to tell you what do I mean by these hexagonal systems or hexagonal mesophases. So if you take the soap or you have soap bar in your home, and if you remove that soap, it has little bit of water underneath, and if you remove that soap, you will see a slime underneath. And if you take that slime and watch it under the microscope, you will see beautiful textures. Okay, these textures come due to surfactant packing. Okay, and they might be lamellar, or they might be hexagonal, or they can be some other type of structure, but they can be characterized very well using small angle X-ray scattering. These are periodic structures, and their periodicity gives rise to these sort of peaks in small angle X-ray scattering, and these peaks appear at a certain ratio of Q values. Okay, by looking at these peaks simply, so for example, this peak is occurring at 0.28 or something, and if this is at 0.45 and this is at like 0.6. So if I just look at the positions of these peaks, the ratio of the Q values, I can, by looking at the ratio of the Q values, I can determine what is the type of hexagonal what is the type of surfactant packing. Here it is in the form of hexagonal, because I'll tell you what are the ratios in the coming slide. Yes, so here it is. So if I have a micellar phase, I have simple micelles in the solution, you will see a broad peak. You will not see any type of multiple periodicity. But if you have a lamellar phase, for example, in the cell membranes, for example, you can see the ratio of the peaks in the ratio 1:2, 3:4, 4:5. Okay, for a hexagonal mesophase, for a hexagonal phase, you will see the ratio in the order of 1:2:2:7. So that is what exactly I was telling you over here. This peak ratio is 1:2 is to 2. Okay, so I can say clearly that it's a hexagonal phase. You can have cubic phases also. Various types of cubic phases are known: primitive, bicontinuous, double diamond, etc. Now, and there are these example from some non-ionic phytenyl ethylene oxide surfactant, which shows these. So this is from this particular paper, where they show different kinds of mesophases which can be formed by surfactants. Okay, I'll not go into details of these, but let's talk about now, for example, now let's talk about nanoparticles in surfactant mesophases. Now this is your general scattering equation. If you remember, I told you n times P of Q into S of Q. P of Q is not F square. Okay, and N constitutes all this. Delta rho is the contrast. P is the volume fraction. V is the volume of the scattering system. Now, this is a nanoparticle, so you have radiations falling on the nanoparticle, and so you can see that scattering of one particle, which is made up of, this is made up of many atoms. It can be explained as an interference produced by all the waves that are sent to the detector from every atom inside the particle. Okay, now summing up of all the wave amplitudes at the detector position and making the square of this sum results in an interference or a scattering pattern. Okay, which is the characteristic of the of the shape or the form of the particle. So this interference pattern which is produced at the detector will be the characteristic of the shape of the particle. Okay. So now, so some time back, I have done some scattering and different types of scattering studies: X-ray scattering, light scattering, and TM studies on spherical nanoparticles. And you can see that this is the SAXS data, which I can fit to 8 nanometer, 11 nanometer, 15 nanometer, and 26 nanometer particles. But I had also got some information about these particles from dynamic light scattering, okay, in terms of sizes, and also from electron microscopy, which told me that it is a spherical nanoparticle. Now, once electron microscopy gave me that information, this is a spherical nanoparticle, I can go back and fit the entire data, the symbols which are shown in open circle, that by a spherical model. Okay, I can use a spherical model and fit my entire data. So I had some information from the TM, although TM did not give me average information. TM gave me only information about some thousands of particles, but there are zillions of nanoparticles in the solution. So whatever information over here about the size I've obtained is the average value, and it corroborates very well with the dynamic light scattering studies. And these are the equation which I was talking to you, a spherical form factor, which has been used to fit this particular data. So I'll not go into details of this, but since I do not want to go into the mathematical part, but a spherical form factor has been used. Now, these nanoparticles can be put in the surfactant systems, these the cylindrical micelles which I was talking to you about. And when I put this, when these micelles are pure, okay, then stacked next to each other, they form these sort of gel, transparent gel. But when I put nanoparticles into it, they can form these opaque gels. And this opaque gel forms because the particles, nanoparticles, are aggregating within the surfactant. Now, these surfactant, the center to center spacing between these micelles can be given by this peak, which is 5.7 nanometer. I can just look at the Q value and I can pull out the D spacing. But if I start putting these silica nanoparticles, which are numbered as 8 nanometer, 11 nanometer, 15, 26, you can see there is this peak which emerges over here, which is a structure factor peak which comes due to the particle-particle aggregation. I can monitor this peak and I can pull out structure factors. Okay, I'll just skip this data and this entire, what I would like to say, this entire aggregation of the particle is going from transparent to opaque is reversible in nature. You take the system to higher temperature, the surfactant system melts, and the particles separate out. Okay, but if I cool the system down, the particles again aggregate and they form the opaque structure. Now, why would it do so? We had actually extensively used small angle X-ray scattering in combination of small angle neutron scattering to understand this. But I see that there is we have paucity of time right now, so I will skip this particular part. But if someone is interested, we can speak about it later. Okay, but what I would like to tell you is another example of liquid crystal and proteins which have been characterized using small angle X-ray scattering. So liquid crystal, again, a class of soft matter. What we wanted to do is to combine liquid crystal with proteins, which we could not do without actually modifying the protein with the polymer layer, amphiphilic protein polymer layer. So this is the amphiphile or the surfactant, which we modified protein with. Now this modified protein was combined with the liquid crystal droplet to form these like composite droplets of liquid crystal and protein. So the idea, of course, is to go and make a biosensor using liquid crystal. And we understand these droplets are very, very fluorescent due to protein labeled with the fluorescent molecule, and they act beautifully in terms of enzyme sensing. But we use small angle X-ray scattering to understand that what happens to the overall structure in this material. When we take these droplets and put protein inside, what we see is that I will just refer you to two curves. So please have your attention on the B and C. So there are two curves in here. So one is the red one, which talks about the protein only. So this shows a broad peak at 57.1 angstrom when there is no liquid crystals. But when we combine this protein conjugates with liquid crystals, you can see that this peak actually shifts to lower Q values. And if you remember correctly, that D was inversely proportional to Q. So as Q decreases, that means D increases. So you are increasing the protein-protein distance from 57 angstrom to 92 angstrom. So what does that mean? That when you include liquid crystal in between protein, the liquid crystal actually acts as a solvent and it separates the protein molecules further apart. Okay, the same happens for the peaks for the liquid crystals as well. So the peaks for liquid crystals occur at higher Q values. So this was lower Q values and this is at higher Q values. So these are the peaks for liquid crystals. And what you can see is that bulk liquid crystal, that is without protein, shows a very nice and narrow peak, which actually indicates it's more crystalline in nature. But when you put the proteins in there, this peak becomes much broader. Okay, and it also shows that the ordering in liquid crystal is getting disturbed as a as a result of the inclusion of the protein. Okay, so we have done extensive molecular dynamic simulation studies to understand the interaction. So, but I'll not go into it right now. Another example I want to give you is, for example, self-assembly of polyelectrolytes. So, for example, one polymer. So, when I say polyelectrolyte, I'm talking about a polymer chain which has charges. Okay, electrolytes you might have understood it's like these are salts which dissociate completely in the solution. Polyelectrolytes also have these sort of these are polymeric chain, but they have these ionizing groups. For example, here shown as NH2. Okay, so if I put it in water at certain pH below 9, they will start getting protonated. Okay, and this is a very specific type of polymer which is known as polyethyleneamine. What we have observed recently, that if I take this polymer and if I put it in water, only the polymer, okay, and if I put it in water and just decrease the pH to 3, okay, we start seeing these beautiful micron sized hollow fibrils. Okay, so these are self-assembled structures. Again, this polymer has a size of not more than 6 to 7 nanometers. That is what we have confirmed using small and DLS, dynamic light scattering. This is the DLS data. You can see the size is between 6 to 7 nanometers. Again, from small angle X-ray scattering, we have pulled out radius of gyration, which is 10 nanometers. And if you remember that I have pulled out this radius of gyration using Gunnier analysis. That is, I take a certain region of this particular scattering curve and I fit it to this equation and find out the slope and get the value of Rg. So the Rg gives me a value of 10 nanometers. Okay, this is for this particular chain only. But if I bring this system to PS3, now you start seeing these fibrils, and the way the mechanism of this fibril formation is that these small chains aggregate to form 100 nanometer particles, and then they grow and they become tubule-like structure, and then they grow further. And that can be monitored using small angle X-ray scattering. And this is what the data which provides you that at PS3, at the initial stages of formation of this fibrils, this 10 nanometer structure Rg actually forms 110 nanometer size objects. So they actually the radius of gyration actually increases. That means they are aggregating in some sense and forming these structures. So this cannot really be probed by electron microscopy in real time. Okay, so based on small angle X-ray scattering, we propose a mechanism that you have initially smaller chains which become larger, and then they elongate and form these bigger tubule-like structures. Okay, the last example I want to give you, only I'll take a minute or so. So we have also been working with something like porous liquid. And this is a new word which can be coined right now, because if you understand, porosity is essentially associated with solids, but there has been a new class of system shown since 2015 or so that the liquids can also have porosity. Okay, so you can make some very small molecules and put them in solvent, and you can put gases in these molecules. But we work with porosities which are in nanometer scale. So these are silica nanorods which are actually hollow. SINR stands for silica nanorods, and we can coat these rods with polymer, and then since these are hollow, we can actually now so once we coat it with polymer, they form this type of system which is actually liquid at room temperature, and we can start pushing gases into these hollow cores. Now this hollowness can be probed by small angle X-ray scattering. Okay, so of course TM can give you this, show you these pictures where you can see a shell, okay, and the hollow core, okay, and these rods are of different aspect ratios, but these are like only tens of particles which you can see from TM. But if you want to get an average value, you can actually use small angle X-ray scattering to probe these silica nanorods of different aspect ratio, 2.5, 8, and 11, and get all these parameters out. You can see shell radius, you can pull out thickness, you can pull out shell length, you can pull out a final aspect ratio as well. So this 2.5, 8, and 11 aspect ratio has been obtained from TM, but on an average, the SAXS gives you different aspect ratio. So that's the average value what you get from, or the realistic value what you get from small angle X-ray scattering. So this was only about the nanoparticle, but we can now go into this liquid and start probing this because this liquid is made up of many nanoparticles. Now the interactions come into the picture, or the structure factor comes into the picture, and we can actually start When I say structure factor, I'm talking about like these two nanoparticles in close proximity to each other. And what is the proximity? Is this D, which can be probed by these sort of peaks which are given here, and we can fit a very simple equation to it to find out what is the average distance between the two nanoparticles. Okay, and this can be obtained by small angle X-ray scattering. I'm sure this information will not be obtained from any microscopic tool. Okay, because for microscopy you'll have to like image the nanoparticles, which will be difficult in this particular phase, gel phase. Okay, so the gels can be very easily characterized using small angle X-ray scattering. Okay, so I'm almost out of my time now. Okay, and at the end, what I would like to say is that it's a very versatile characterization tool, small angle X-ray scattering. I can use for various types of samples, liquids, solids, powder, gels, glasses, aerosols, or semi-crystalline polymers. Various types of sampling environments are possible. We have this facility at our institute and can be used for various kinds of analysis. With this, I would like to end my talk and would like to take your question. Thank you.
Thank you, Professor Sharma. That was quite an informative talk. We have certain questions lined up for you, Professor Sharma.
Yes.
Okay, so the first question is from Shubhankar, RGIPT. Is it possible to visualize condensed polymeric zones of few nanometer size inside of hydrogel matrix?
So yes, if there is a difference in the electron densities of those zones. Okay. So it is possible. So the type of systems you are talking about are biphasic systems. Okay, and if there is a difference in these, the electron densities are different of these materials. Of course, when there is a phase separated stuff, then definitely you can visualize these. Yes,
Okay.
you can. Yeah, okay. And you can always pull out what are the length scales of these phase separated domains.
So the next question is from Prem Goyal, Pillai College. The user is asking, we have prepared nano composite where ferric oxide nanorods are embedded in a polymer matrix. Can we use SAXS to find out if rods are aligned or not?
If the rods are aligned, okay. Yeah. If they are, that's a very good question actually. You can actually do that. So of course, when the system is isotropic in nature, you will see a diffuse scattering. You will see a like the concentric rings, or you'll see a diffuse rings if the rods were aligned in all the directions. If they are aligned in only one specific direction, you will see like more scattering in a like you will see anisotropic scattering. Of course, you can do that definitely. Yeah, so that's how the lot of liquid crystals are also analyzed. Yeah, you can do.
Okay. He has added to that question one more question, that we are trying to align the rods in a direction perpendicular to the surface of a polymer film.
Perpendicular to the surface of? Sorry, I missed your.
Polymer.
Polymer film.
Yeah.
Okay, so that is what you want to analyze. So maybe you have to do what is known as grazing incidence small angle X-ray scattering to analyze the system. It can be done, but not in the transmission mode, maybe in the reflection mode. So I didn't give you any example of the.
You're saying
we have, if you remember that I showed you a lot of accessories which are available with our machine, and one of those accessories is grazing incidence small angle X-ray scattering, and that can be done. Yeah.
Okay.
So all the examples which I have provided is on the transmission mode, but of course these can be done on the reflection mode as well.
Okay. Another question is, how SAXS can be differentiated by X-ray reflectivity of thin films?
Oh yeah, so this is the same question going back. So when we are talking about reflections, we are talking about grazing incidence small angle X-ray scattering only. So when you say SAXS, basically like we presume that we are talking about transmission mode. We are asking that there is a sample and your beam is going to go through the sample. After getting scattered, it is going to follow. So when you are talking about reflectivity, you are taking sample like you are like you are in a certain direction. You mount your sample and you are looking at radiation falling onto the sample and getting reflected. So that's your actually reflectivity measurement. So all the examples what I have provided in my talk were based on transmission mode, but of course X-ray reflectivity will also give you the type of, like for example, the previous person was asking about how to, if they want to align the rods in on a polymeric. So definitely they'll have to do the reflectivity measurements.
Okay.
Or,
Next.
or in other way, this is known as grazing incidence small angle X-ray scattering.
Okay. Next question is how to find out the disorderness of polymer using SAXS analysis.
Okay, but I didn't get this complete question. Disorderness in the system. So is your system having some sort of liquid crystalline phase?
The user has not mentioned, he has just written.
Yeah. So I assume they are talking about some sort of partially ordered structure. Okay. If they want to find out what is the coherence length or what is the correlation length in their system, they can do something which is known as a Debye-Scherrer analysis, which can provide you what is the coherence length or what is the crystallinity in their sample. Okay. So, for example, this is lot done in the case of semi-crystalline polymers. Okay. So I suppose that was the question because they wanted to understand how much their sample is disordered. Okay. Or in other words, should I say how much it is ordered? So, or what is the the length scales of that order structure. So that is what we can do using something which is known as a Debye-Scherrer analysis. Okay.
Okay. One more question, sir. Why in SAXS of polymers we get a peak at the very beginning of a plot that is common in all polymer at different scattering vector?
Okay. So I presume that you are talking about beam stop. Okay. At the very beginning, of the what does it say?
At the very beginning of a plot that is common in all the polymer at different scattering vector.
So at different scattering vector, they are getting peak.
Yes.
I would just like to show them a video. Can I share or no? I'll not be able to share, right? Okay, so at initial Q values, you always get a peak, or at very low Q values, you always get a peak because of the beam stop. Okay, and so one should remember in a scattering experiment, only very small part of the beam gets scattered. Okay, the a majority part or a very high intensity radiation remains unscattered and it falls on the detector as such. Okay, that's known as the primary beam. Okay, and that primary beam has to be stopped directly falling on the detector with so that the detector doesn't get damaged. Okay, and the way it has to be stopped is using some sort of absorber. For example, in many instruments it is used as lead, okay, or something like that to absorb these X-rays. That's known as beam stop. If there is some leakage out of the beam stop, you will see some sort of peak. Okay, you will always see a peak irrespective of any sample. Okay, so your beam stop should be very well aligned. So that's a part of the instrumentation that when you do an experiment at very low Q value, you will always see a peak irrespective of if your beam stop is not aligned, irrespective of any sample you do. Okay, so you should not see any peak at the starting of this any sample. Okay, if it is a part of the sample, that's fine. But if it's coming in all the sample, then it is an instrumental artifact. Okay, and it has to come from the beam stop only.
Another question is, how can I find the pore size of a material using SAXS data?
Okay, so pore size, of course, you'll have to do, that's what I told you. that if you have to look at the pore sizes, for example, you have to do some bit of analysis. Okay, if you have, for example, you have particles which are porous in nature. Okay, and there is like so you can assume that pores will have walls. Okay, pores will have walls, and these pores will be connected to each other, right? Okay, now if I look at the scattering from the pore, inside the pore, the electron density in the pore is very less, or in the area. Okay, but as the scattering from the walls will be pretty high from the material, but then you go ahead, the scattering again becomes low. So there'll be a certain scattering pattern which will be generated, which actually which is characteristic of the orderedness of these pores. Okay, so you can actually look at the data and try to look at some sort of correlation peaks, which actually tells you that this is the sort of length scales how these pores are actually placed. Okay, or they are ordered in some way. So based on that, you can find a center to center distance between the pores. Okay, and that can give you some idea about the pore size. Okay, so exactly finding out the pore size from SAXS data can be tricky if you don't know that if your pores are not ordered, well ordered. Okay, for example, I have these like very nice mesoporous silica. Okay, now in mesoporous silica, you can have these pores very well aligned or very well ordered. So it will give us some sort of diffraction peak, okay, or some sort of scattering peak due to due to some sort of orderness in the material. And the length scale, or at the Q value at which these peaks arises can give you the idea about the dimension or the center to center distance between these pores. Okay, and that will give you the indication about the pore size. So by the way, the Q value is equal to 2 pi by d in most of the materials. 2 pi by d is approximately.
Okay. Which is the best software for data analysis?
There are a lot of routines right now, and there is something which is known as SAXS. Okay, SAXS is one. I don't know if I have it over here. Yeah, there is one SAS data analysis, SAS data analysis. Okay, there are also inbuilt routines in Igor, which is available from NIST website. Okay, so but you can try SAXS, SASFIT, SAXS.
Okay. One more question. How does one take care of the multiple scattering effect in the solution phase X-ray scattering data analysis?
Okay, very good question. Actually, this comes from the question I was talking to you about. What is the optimum length of the material, or what is the optimum thickness of the material which needs to be taken? Okay, so you should be just below that optimum thickness. Okay, and if you are worried about multiple scattering, of course, you should be below the optimum thickness, and you should have a dilute solution. Okay, so that's the best way.
Okay, so that's it from our end. We have next upcoming webinar on sample preparation solution on 4th November. Registrations are now open and the link is listed on our website. Thank you, Professor Kamendra Prakash Sharma, for giving us your valuable time and delivering us a talk. A special thanks to Professor Anil Kotantrayal for initiating this webinar series of instruments placed in our SAFE IIT Bombay. Thank you, Dr. Gajendra Saini, for all your support. Thank you, our IT team, Mrs. Nidhi Goyal and Jagdeep, for your technical support. Thank you, all the participants, for making this event successful. Stay safe, stay healthy. Have a nice day.